Welcome everybody to Green Chill's webinar for the month of August. My name is Keely Whitman, and I run EPA's Green Chill Partnership. We're happy to have you. Thanks very much for coming. The webinar today, I'm going to start off with a little bit of an explanation about webinar logistics. I'm going to do a very short introduction to Green Chill. And then I'm going to just briefly go through the results of a survey, an email survey. It wasn't anything particularly official that we did last year, where I polled the Green Chill partners to ask them about their fears or hurdles or concerns that they could think of related to, at the time it was both CO2 refrigeration for supermarkets and ammonia refrigeration for supermarkets. So I'm going to show you some slides on the results of that survey. And then we have a speaker who's going to present ammonia's environmental benefits and ammonia performance and some solutions to the challenges that we found in the survey. His name is Caleb Nelson. And then we have Eric Smith from the International Institute of Ammonia Refrigeration, who's going to be presenting example ammonia technology for supermarkets. So just in terms of webinar etiquette, the webinar is being recorded, and it will be available on the Green Chill website under Events and Webinars in a couple days. I am going to centrally mute everybody's line so that we don't get any noise or the feedback that tends to happen when you have this many participants. So once I do that, all of your lines will be muted, and if you want to unmute your line in order to say something, you are going to have to press #6. So I'm doing that now. That
has muted your line.
That works to mute everybody's line. Can everyone hear me still? Oh, I can't answer because you're all muted. Can I get my presenters to press #6 so that you're unmuted?
Yeah.
Okay, you hear me. All right, good. I didn't want to, continue for a half hour and find out that I had inadvertently muted myself. So, all right. And Eric, you're going to have to press #6 also in order to unmute yourself so that we can hear you. For other participants and attendees, we are going to have a 30-minute question and answer period at the end of the webinar. And of course, you are free to stay for that or not to stay for that. We, of course, encourage you to do so. All Green Chill webinars are meant to be interactive. We're not, professional webinar presenters, right? That's not our specialty. And, so these are very informal, and sometimes we have technical things that go wrong, and that's just a part of it, because I prefer to spend my time doing things for Green Chill than spend my time becoming an expert in the WebEx technology. But if you look in the lower part of your screen to the right, there is a little button that has a hand on it. Because we do have so many people participating, if you have a question, please click on that little button, and you can go ahead and try it out now if you want to. I'll see, just on my screen, I see hands up here. There we go. I saw there, Nick, I see your hand. Ryan, I see your hand. And then to, of course, signal that, your question is over and you don't have another one, you have to, Billy, yours, you have to press the button again to make your hand disappear. So, other than that, if possible, if you have a general question for discussion, I'd like to ask you to hold your questions until the question and answer session at the end. That would be very helpful. because otherwise with this number of people we'll never get done with the actual webinar. Just a very quick introduction to the GreenChill partnership. GreenChill has 3 main programs. The Corporate Emissions Reduction Program, that's when you hear about GreenChill partners, supermarket companies that have become partners, those companies have signed up for the Corporate Emissions Reduction Program. They measure their refrigerant emissions annually, and they set goals annually to reduce those emissions. So we do have 50 partners, I'm very proud to say, and our 50th partner is from our nation's 50th state, Hawaii, a company called Down to Earth, and where I'm not sure why, but I consider 50 partners to be some kind of a milestone, so very happy to have reached 50. Next program is the Store Certification Program. It is a program where GreenChill has set specific criteria that an individual store can try to achieve, and the criteria mostly have to do with refrigerant size reductions and refrigerant leak rate reductions. And we have a silver, gold, and platinum certification levels available. So we already have, I believe, 46 certified stores in the nation. It doesn't seem like a lot considering that there are over 35,000 stores. You don't have to be a GreenChill partner to get your store certified. We're a little over the program's a little over a year old, so you know, I think we've made a lot of headway in terms of getting recognition on a store level. The third program is the Advanced Refrigeration Program, and that is where we share information to promote the use of advanced refrigeration technologies, strategies, and practices. And our webinar series is part of the Advanced Refrigeration Program. So why is GreenChill having a webinar about ammonia refrigeration for supermarkets? Well, our mission is to reduce refrigerant emissions from supermarkets and decrease their impact on the ozone layer and climate change. So our motto in terms of how we advise people to go about that. Mute everybody's line again. I'm getting laughter in the background. That means, though, that because I think everybody who joined just recently isn't mute, so that means, unfortunately, my speakers are going to have to press #6 again. Okay.
Okay, I'm with you, Carly.
Okay, great. So, in terms of how we advise partners to go about achieving that mission, we concentrate on reducing refrigerant charge, reducing leaks, and we advise companies to use the lowest the refrigerant with the lowest global warming potential possible in order to still meet your performance needs. So, as you know, philosophy, we think it makes sense for the environment and it makes sense for your bottom line. Obviously, ammonia, we don't have any supermarkets yet running on ammonia systems, commercial refrigeration ammonia systems. It's obviously a very low GWP refrigerant, so thus it makes sense that we look into it and try to share information with the stakeholder community about it. As I mentioned before, GreenChill did a survey to try to collect the ideas from our partners on some of the hurdles that will face ammonia commercial refrigeration for supermarkets. And I'm not going to go through and read all of these to you. You can obviously look at your screen and read them yourself. But I do want to just point out that this is just a reflection of the answers that I received to the survey. So some of these are real hurdles, some of these are perception. Caleb, the next speaker, is going to actually go through each one of these and talk about each one of these individually. So I'll go to the second page. It's just 2 pages on the survey results. So basically, things like the different end user needs and lack of service technician experience, some of them are easier to overcome than others, but we're going to discuss all of them. So I'm going to hand over now to Caleb Nelson from TA Architects and Engineers, and he can I just ask? I think Bill Shuttlesworth has his hand up. Did you mean to? Do you have some kind of a question? Oh, there we go. Okay, put your hand down. I just wanted to make sure that you were still with us. Okay, Caleb, you have control of the slides. Thanks very much for being a presenter, and I look forward to hearing what you have to say.
Thanks. Can you hear me?
I can.
All right. That means everyone else can too. Yeah, like you said, I'm going to be going over the environmental impacts of ammonia and try and look at why we would even talk about using ammonia in the first place. And then beyond that, I'm going to look at some of the performance factors of ammonia, and then also, like you said, go through some of the hurdles, or go through all the hurdles and try and look at some of the challenges of those and what maybe some of the solutions are. And if anything, be able to provide some perspective, hopefully, if anything, on some of those. So, said why ammonia even begin with? I guess first of all, it's a natural refrigerant. It has a 0 ozone depletion potential and a 0 global warming potential. The reasons that you would use ammonia for these reasons based on attempt to be green, and then also some folks are concerned about future legislation and what that means. I know there's a big debate on global warming going to be the next that's rated, since current depletion is being regulated. And beyond that, efficiency is the next item that you want to use ammonia. Energy prices aren't dropping; they're not expected to drop. So if you're not looking at environmental reasons, it's a cost thing, an operational cost thing. And there, the TWE factor, which is the total equivalent warming impact, and I put that in there because it's important to look at the efficiency and the global potential. There's where you go into an existing store and you put all the direct expansion racks and you pull the HFC back into the compressor room and you limit your HFC charge, and a secondary system in, and if you're careful, it would probably be tough, but you could end up in a worse scenario environmentally than you were to begin with if your pumping costs and your pump gives you a less efficient system, since most of the contribution to your footprint can come from your energy side. So that's why it's important to look at both of those if you are truly aiming for a green store, not just look at the ozone depletion and the global warming. There's the philosophical debate: should we stop leaks or should we just use a low global warming potential refrigerant? I wasn't going to get into this, and great, just got some bullets to think about. What is the possibility of fully stopping leaks, and what happens when systems are upgraded or they expire if refrigerants do end up coming out that are more efficient, or we even want to reclaim some of the older refrigerants that are in stores. So just kind of some things to think about there. Look at the environment. I put down kind of some things to make you think about ammonia and how it is actually emitted into the environment right now. It does actually get emitted into stack emissions, like at power plants and things. Injected into the air, into the stack emission stream to neutralize other harmful gases. I think it's oxide and nitrogen oxide are some of the chemicals that ammonia will actually neutralize. Beyond 15 million metric tons are produced in the U.S. every year, and percent of that is used agriculturally. So as a fertilizer, it'll actually get into the ground, and you can take a size of land about an acre size, and they'll link up to 150 pounds of liquid ammonia into the ground over a year's time. So it's a pretty big. It's a pretty big if you look at pounds of ammonia that are getting put into the ground every year, just from agricultural reasons. Biodegradable, which basically means that it has a short life in the atmosphere. I guess a lifetime altogether. I think it's a number of days until ammonia fully decomposes in the atmosphere. The body actually releases 15 grams of ammonia every day. That's the average number through the natural chemical processes in the body. And also, we can look at what happens when ammonia gets burned, and the byproduct of ammonia is just nitrogen and water, and that's a pretty big difference than if you look at what happens when you burn a fluorocarbon refrigerant, and that's it, and the phosgene gas and carbon monoxide that it can produce. Moving on, ammonia's performance is the refrigerant of choice industrially, and I hate to use the word industrially because as a fellow commercial retail refrigeration engineer, we know that industrial systems are completely different than commercial systems, but it's still important to show here. If you look at the size of some of the industrial systems out there, you know, they can use anywhere from 50 to 200,000 pounds of ammonia, and if you kind of, you know, they're not just going to put any efficient refrigerant in systems that are that large. It's got to be a proven refrigerant, a proven technology, and so that bullet in there. But with saying that, ammonia is now being used successfully in supermarkets in other countries, so it started to bridge the gap from industrial to commercial. And all those in the U.S. currently, there are other supermarkets that have used it successfully and have been more efficient in that, and I've been able to do so safely as well. This third bullet kind of goes back to what I was talking about with the total equivalent warming impact. You know, there is opportunity with using ammonia to make up for and exceed some of the possible efficiency losses that you can see with secondary pumps. And it does give you an opportunity to make up for some of that. And then the next slide, hopefully I can kind of about one of the reasons why ammonia can be more efficient. Kind of the biggest thing, and there's a lot of different science, and you can spend a lot of time on this, but the biggest property is the vaporization heat of ammonia. Let's contribute to its great efficiency. Because of really low mass flow, and high index of compression, there's a lot of vapor that's produced when you evaporate ammonia. So all the vaporization heat of ammonia can be 9 times the vaporization heat of R12, and up to 3 times the vaporization heat of CO2, 404A, R22. Those refrigerants, you're not going to see 3 times the efficiency or 9 times the efficiency. There's factors in there, and one of the ones is the amount of vapor that is produced. All that has to be compressed again. So some of that's dampened by the compression required. In the end, I know it's kind of vague to say this, but in ammonia does prove to be a superior refrigerant efficiency-wise, and that's not typically debated. One of the factors that plays into it is the factor of copper. Ammonia, when it comes in contact with copper, is a precipitate inside the system, which is not a good thing, and so that affects your heat exchangers, affects your compressors. Obviously, you got to use like a steel heat exchanger. That's the most common, is a stainless steel heat exchanger. They do make copper heat exchangers that are they've got on them to protect them from the copper that you can get more efficiency out of those. And compressor, if you look at a standard FC rack with semi-hermetic compressors, the suction gas flows over the motor windings, which are copper, obviously, and cools the motor. So that's one difference, is you would need to use an open compressor to that. And I under ammonia's performance because it's kind of a catch-22, or I guess maybe it's a little ironic that using the open drive compressor actually gives you a little more efficiency to your system because you're not that extra motor heat in your suction gas, which is up as a heat or rejection condenser. So by having the open drive compressor, your motor is just free to cool itself with the air around it, and that doesn't end up in the system. So it's a bit and a negative at the same time. And I'll go later, but there are some recent compressor technology it's where they have used aluminum windings for a hermetic compressor, and has been successful. There's a little bit of efficiency that you get by with aluminum windings versus copper, but drive evaporators, I don't want to get into a huge tangent here, but both used with ammonia systems, and there's some efficiency and kind of factors that play into that. With flooded evaporator, that's probably the most typical evaporator you can see with ammonia systems today, and even smaller systems can get more efficiency out of the evaporator because every inch of the surface area evaporator is actually used to boil refrigerant instead of superheat it, and that into the low superheats that you get back at the compressor, which kind of makes that whole cycle more efficient. And with any with chiller, you can float the head a lot easier than you can with the direct expansion system. So with the flooded evaporator, it's got a more mild expansion, which makes it easier to float the head down and get a lower pressure on the liquid side. I put oil management there because the oil management, the service demands are a little different with the dry evaporator versus the flooded evaporator. But we don't really go into that right now because it doesn't have a lot to do with the performance. Now I just kind of reiterated some of the hurdles that he showed, and I won't read through these either because I'll slide on each one of them. So they want to look to see what a solution is. Is the hurdle even real, or is it just something that's perceived? The first one was the multiple code and regulation demands. First, SNAP has already approved ammonia for commercial use as a primary refrigerant in secondary applications. So that's something that's already been done at this point, and it's not something that's going to have to, like when CO2 first started, that was a process that had to overcome before it could be used, and that's been done with ammonia.
Caleb, sorry to interrupt, just so that I'm not sure that everybody knows what SNAP refers to. It's an EPA program that finds substitute refrigerants for ozone-depleting substances acceptable for use in the United States. So it's an EPA process that a substance would have to go through before it's allowed to be used, for instance, in this case, in supermarket refrigeration. Caleb said for CO2, when we wanted to start with the first CO2 systems for supermarkets, the first thing we had to do was get through the process to get it approved by the SNAP program. And the point is here that has already been done for ammonia, so that is already solved. So again, sorry, Caleb, to interrupt.
No. We've got the international code pretty extensively, and there are major deterring restrictions found in the international code for a rooftop ammonia chiller. You can get in a machinery room, but you would be limited to all the requirements of a machinery room, and so it's really the most feasible way to do ammonia in a supermarket is to put it in a unit on the roof. And Eric's going to talk more about what that's going to look like, but basically it wouldn't even be a a doghouse on the roof with the chiller inside. It'll just be an outdoor system with removable panels for maintenance. It really would be truly an outdoor system. The IC and ASHRAE 15 allow the classification of a low probability system if it is outdoors. So just kind of reiterating why we would put it outdoors, some of the benefits to that on the code side of things. There's a section in the international code that talks about diluting, diffusing, or burning ammonia upon the event of a discharge. And AR, which is the International Institute of Ammonia Refrigeration, and ASHRAE both prefer a direct release into the atmosphere through the pressure relief valve. They will not see diluted, diffused, or burned. As long as it's acceptable release, it's better to just give it straight to the atmosphere. And the international code does say that upon review of a technical report submitted by a professional engineer, you don't have to do any of those three things as the fire official signs off on it. And like I said, it's not even the preferred method, so it's just kind of in there, and I think it's actually I think the IR is actually working to get that removed. But mostly that would not be a requirement.
If I could interrupt for a moment. Diffusion.
Please.
Diffusion tanks are a requirement of the International Mechanical Code, actually the International Fire Code, and the Uniform Mechanical Code. What they are is a tank starter that would supposedly capture vapors that are released of the pressure relief valves. There are a number of historical problems with them, and their development was really 40 years ago when 40 or 50 years ago when emergency operations weren't really well understood. It's one of several options for dealing with the possibility of an ammonia release in a densely populated area. But in any case, it's significant to note that the preferred method is discharge to the atmosphere, and it is typically considered inconsequential method. So back to you, Caleb.
Thank you. I did mention that there are some states and counties that have adopted their own local codes that can be more strict on ammonia through in just New Jersey, LA, and Chicago. And these haven't been researched. I do know that there are plenty of systems in those areas that have a lot more pounds of ammonia in it than we would see in a supermarket. But kind of the point of saying that is that there's areas that strictly just go by international code, and I mean, in opinion, but starting out with ammonia, it makes sense to populate those areas unless you wanted to do the footwork to figure out what are their extra regulations on those systems, and does it make sense just to put it in a different area? So you could research every code, every as well, and look for that, but it's the majority just go over the follow international code. Next three bullets here are basically came up on the survey that Keeley did. One of them was the requirement to need an engineer on site, basically 24/7/365, and that is not a requirement. So that is a good example of misconception. With OSHA's Project Safety Management Plan and the EPA's Risk Management Plan, Those are required for systems with less than 10,000 pounds of ammonia. And so I should mention, but a supermarket-sized system would have probably 200 pounds or less. So, and they take until 10,000 pounds. So another, again, another misconception there. I want to note that there is a leak reporting trigger. If you leak 100 pounds of refrigerant or more within a 24-hour period, you'll report that to CERCLA and CRA. And I know what those are. CERCLA is Comprehensive Environmental Response Compensation Liability Act, and the EPC is the Emergency Planning and Community Right to Know Act. There talks a little later about what the system's actually going to look like. There's a good chance that we're going to have, you could either one module that would be ammonia chiller that could basically take care of the entire store and have less than 200 pounds. You could break that up into smaller chiller units and basically be under, each chiller could be under 100 pounds, and so that wouldn't even be a possibility that you could leak over 100 pounds. Obviously, two of your chillers leaked at the same time, so it's just important to note that. Move to system costs. I would say this is probably one of the hurdles that is a hurdle, just because there are economies of scale yet with ammonia commercially. And it is important to note that it is only going to apply to the high side. So everything in the store, you do a secondary system, so your pump skid, your cases, all your distribution piping inside, none of that's going to be affected by using an ammonia system. Basically, you take a standard secondary HFC system, pull the and put the ammonia on the roof. So the cost that is going to be greater is going to be limited to just that high side of the system. And as there's no economies of scale yet, and kind of to get that is to prove the demand for manufacturers to really start putting them out. So I think we've seen the same hurdle with CO2, and I think that we're seeing quite a few CO2 systems getting put in all over the place, and so I think it's something that is a hurdle, but to get through. This is one that's going to be cheaper just due to the fact that ammonia is very cheap in comparison to a fluorocarbon refrigerant. Obviously, 80% of the 15 million tons of ammonia that's produced is used agriculturally, and so the cost refrigerant is somewhat set by that demand. You're not going to be able to steer ship away from that very easily. So if you start using ammonia commercially, that price is it's pretty low, and it's low. So also, expected that any low GWP refrigerants that become suitable for use in the future would be especially expensive. So is one of the other hurdles that was brought up. Excuse me. Ammonia is a really good refrigerant. It's been basically in constant use for over 100 years. So there's some equipment manufacturers, even in the United States, that produce all kinds of different components for ammonia systems. And they do tend to cater to larger components due to the fact that industrial is the main use for ammonia right now. But there are components that are accessible to commercial manufacturers, and it's really about time before commercial manufacturers start building their own systems. So we know that they are looking at doing, they're considering ammonia systems at this point. Humility is another hurdle that was brought up. And as far as familiarity goes, I mean, ammonia is going to be used in the same refrigeration cycle. The pressure actually going to be very similar to an HFC system. The contractor's going to, it's going to be in his ballpark of what he's thinking on for pressures. We use reciprocating compressors just like we do now in supermarkets. Screw can also be used, but they're a little better suited for larger applications. An in-depth subject there on when you would use a screw over a reciprocating compressor, but it just needs to be noted that reciprocating can be used and probably will be a tendency in the commercial systems that come out. The only difference, like I had previously mentioned, is that they will be open drive, and it is important to note that with all the secondary systems going in now, that factor of aligning shafts being dealt with secondary pumps. So, that's something that the technicians are already dealing with. I kind of already mentioned this before too, but the advancement in compressor technology with a hermetic ammonia compressor would alleviate that. This is a hurdle. It's obviously not perceived. I think it's a real hurdle. I think if you look at the rate of implementation of ammonia, probably going to be more of a gradual, just like CO2. It's going to be a gradual introduction into the market, and I think short term there's going to be. I think you're going to be getting some of your more experienced contractors, and although rare, there are some commercial contractors out there that do work industrially, but I think long term might be more of the look at, just as you start more and more ammonia systems. Now you're pulling from a broader range of contractors, and the question is, are they up to speed with ammonia? And once again, this is something that we've had to go through with CO2. So although I think it is once again something that could be overcome. And there was a note that Keeley put in there with on the chemical companies for a lot of training. And I think we've already seen a shift training to manufacturers of CO2. So I think it would probably be the same suit there. Some of the design, installation, and service demand items. As far as the design goes, I think a lot of it is going to be mainly focused on the secondary portion of the system, just like we've seen with going secondary HFC systems and CO2 systems. The chiller is going to be assembled in the factory because we want the tightest factory-built ammonia system that we can get, and so it's basically, as far as the ammonia side, it's going to be a matter of probably just sizing the compressors and the heat exchangers, which would put no real new design demand. I think a lot of for a lot of refrigeration engineers, it's been more the hydronic side that's required almost more heat on the design for that. Like I said, in order to ensure that every weld is good, in order to ensure that all the piping runs are as short as they can be, everything's going to be built in the factory. Either going to be, you're bolting two skids together, or it's all going to come on one skid. Basically, the most factory work that we had is equals the less field installation. So I think because of that fact, it's not always a very big hurdle for the installation, design side of things. As far as it goes, there will be maintenance, just like any other system, and system action, and that should be provided by the equipment manufacturer on what needs to be inspected, what needs to be maintained routinely based on what type of system comes out. There's many ways you could do an ammonia chiller the size we're talking about. It really is, you can't talk about now really. You you got to get them to manufacture later, but shouldn't be any increase in service demand. If there is an increase, it's going to be insignificant for applications this size. And then as the compressors go, I mean, we're still going to have multiple compressors. So service on compressors would be the same as far as isolate compressor and not having to shut down the store or the entire system to do maintenance. Some systems do use very large screw compressors, and they've got one compressor for the whole system, and so it's a little different story. But we still would probably be looking at using multiple compressors. And the biggest thing is just the contractor becoming familiar with the safe work practices for ammonia. And like I said, that's the same scenario CO2. Data, this is a hurdle, but I think it's true. There's no U.S. supermarkets operating with ammonia yet, but you noted that there are supermarkets, as I mentioned earlier, that are operating in other countries. I just kind of threw in a quick little example here of a supermarket in Hungary that was fitted with an ammonia CO2 cascade system, and I read that there's some efficiencies seen from both sides of that cascade system, but throw it out there, they were seeing, the contractor was measuring the energy usage through some summer months, and they were seeing 35 to 38% energy consumption in those months. And so it was just, they did it to a 404A store of the same size. So not a in-depth comparison giving you there, but I just found that it's been done and that there are energy savings that have been seen. These fears relating to ammonia's toxicity and flammability. Again, just to remind them that it's going to be a secondary application, so there going to be any ammonia contained inside the supermarket. So any leaks noticed by any shopping customers. And then that second bullet there, 200 pounds versus 200,000, is just kind of a relationship of a supermarket charge versus an industrial charge. Not industrial charges are that large, but 50,000 pounds is a lot more than 200 pounds. So the ammonia gas density, it is lighter than air. So if ammonia gas is leaked, it will rise and get diffused to the air versus concentrating as it pools. So, and then the other item there is the odor, and I put parts per million there just to kind of highlight some of those some key levels. Parts per million is when you can detect ammonia. Is when you can detect ammonia with your smell, and then 300 parts per million is about the point at which you're not going to be hanging around. You're going to be getting out of the area, and so you've got those two warning steps right there, and then beyond that, it's not 2,000 to 5,000 parts per million with exposure of more than 30 minutes before you can start to trouble. So hard to know that. And if you think about ammonia on a roof, that's going to, because it's light air, it's like that, it's going to be a little insignificant there. But regardless, the plume model could be done fairly easily if there are still, if an owner still wants to put any fears at ease, and you can look at concentrations and the duration of exposure at different by modeling your worst case scenario. And I think that'll be something that may be done on some of the floors, but I think that it's going to a point where everyone's going to be pretty confident with what that will look like, and it's not going to be something that's going to be needed. Flammability. Ammonia is considered non-flammable in an outdoor application because it must be confined to catch fire. And since we wouldn't be using a doghouse on the roof or a rack house, really truly would be an outdoor rack, be considered a non-flammable refrigerant at that point. Be that looking at the parts per million that you would see on the previous slide, this would be 1,000 times that, and that's the 2,000 to 5,000 range, considered flammable. And then, kind of as another fail-safe, leak detection would most likely be used on that rack, and since it would movable panels, refrigerant could get inside that panel, but there's going to be natural ventilation through those walls, and even if the filtration did get to a dangerous level, leak detection would know that, and there would just be a very small exhaust fan on there to pull that refrigerant out into the atmosphere. This is something, kind of some data that was collected, and it just kind of gives a little bit of perspective on the state of ammonia, and I'm not going to read it, but the lethal accidents were recorded in the USA, Denmark, Finland, Norway, and basically it was given an annual death rate of less than 2 per billion population per year, and these are basically industrial systems that are giving this data, so systems with thousands of pounds of ammonia. And just as a benchmark, the annual death rate of lightning strike in the USA alone is 32 per billion. So just to kind of get some perspective there. One of those that was received is a lack of guidelines for safe implementation of ammonia. Ocean EPA, once again, they've got their PSM and their RPM programs that we talked about earlier that aren't required for systems less than 10,000 pounds. Very in-depth safety guidelines that, like I said, aren't required for supermarket systems, but nonetheless, there's guidelines there that can be used if the owner if the owner wants to use them. IAR has their ARM program, which is targeted for systems with less than 10,000 pounds. And I will talk more about this, but in that guideline as well that can be used. And then so the IAR2 and the ANSI codes and ASHA 15 are further codes that deal a lot with ammonia. So I would say that there's definitely a shortage of guidelines for safe implementation. Applicable for conversions and remodels. Might be a solution for a conversion where you would drop in the refrigerant, mainly because of their reasons and also because it would need to be applied in a secondary system. And so it kind of throws that out the window. But for models, I think, is probably where there's the most opportunity to use it. There are remodels that are already moving towards secondary systems, and as I mentioned earlier, you've got an HFC chiller applied to that system, and so basically instead of applying that HFC chiller, you could apply an ammonia chiller. Nothing inside the store is affected by using ammonia. That's all taken care of by the secondary, either CO2 or glycol side of the system. I put expansions down there. You could use, depending on what size systems commercial manufacturers start building, if you did an expansion, you could smaller chiller and just take over that new area. However, I don't know if that will ever be done. I think you'll get more bang for your buck by applying ammonia to the entire store and educating it with CO2 DX on the low temp side, or smaller CO2 secondary on the medium temp side. Limited location. I guess just real quick, there's lots of downtown ammonia systems in Chicago, for example. There's large ammonia systems in busy airport terminals, et cetera. So ammonia in many different locations, and it seems to kind of reach different types of areas. And as before, there's lots of ammonia systems on roofs of other buildings, and so, the supermarket is different than a roof of any other building, really. So, and a plume study always be done if there is a doubt on the location. And I think this is my last slide, but the end user needs. One of the issues that came up with Keeley's survey, and kind of the question was, for supermarkets, do we want, since ammonia systems are more industrially, do we want a real durable ammonia systems, or do we just want a cheap 10-year system that we're going to replace every 10, 15 years? Does it apply to supermarkets? And some of there were the fact that ammonia is on the high side, and so you've got this secondary system inside the store. You can touch the sales floor all you want. You don't have to touch the ammonia system. And so really the longer your ammonia system lasts, really the payback, and it is future-proof because it's unlikely that any legislation would phase out a natural refrigerant as long as it continues to be safe and efficient. So really, once you get to the ammonia step, you want it as long as it can. So I see that any supermarket would want a system that was only going to last 10, 15 years when they can get to the end of the road with ammonia and have it last longer. So, and really when it comes down to maintenance too, is it going to maintain the ammonia system just like they do their HFC systems, or are they going to give it more maintenance to make it last longer? So there's a lot of different variables in there. So I think that's all I got.
Okay, thanks very much, Caleb. I'm going to hand over to Eric Smith, the Technical Director for the International Institute of Ammonia Refrigeration. Before he starts in, I'm not sure if I said this at the beginning of the webinar or not. I want to make sure that everybody knows that Green Chill holds these webinars. The purpose is to encourage knowledge sharing, information sharing, interaction among Green Chill stakeholders centered around a topic of interest that we've heard about. Green Chill doesn't advocate for any particular technology or refrigerant. We think the market is served best by having as many options as possible so that each store can pick and choose what is the best solution for them. So I want to make sure that people understand that these webinars aren't promotions for a person or a company or a particular technology or refrigerant. I'm sorry if I did say that at the beginning. I can't remember if I said it or not. So better to repeat it. Eric, go ahead. I've handed over to you.
Thanks, Keeley. My presentation is not nearly as long as Caleb's, but my goal is to show you both theoretical and actual layouts of ammonia supermarket systems. So I'll get into it a little bit, and I have just a few comments to make here along the way. Let's see. Just make a couple of events here. Okay. All right. So as Caleb was indicating, in these applications, the ammonia would have to be the primary loop refrigerant because it is a B2 refrigerant, and therefore it needs to be contained remotely from any occupied space. doing this, we would be able to obtain the lowest charge possible. The systems would, as Caleb indicated, be located on the roof, and of course, designers would need to be sure that ventilation systems for the supermarkets, various fans for ventilation, docks, etc., would be away from the systems, and this would create the lowest maintenance possible. So regarding tech training, the idea is that manufacturers would be able to train and up-and-coming contracting companies and service companies with practices of ammonia, just like they currently do with HFCs and CFCs. And as far as emergency responder training, recommends for industrial systems and would also recommend for the smaller systems that the contractor get in touch with the local fire department and just let them know what's going on, and also them know when any service work is going to be done. This is mainly an attempt to panic and just to keep everybody informed. With small large systems like this, it's probably the case that, if there were a big leak, it'd all be gone by the time they got there anyway, and there would be nothing to do. But in any case, it's good to keep your local hazmat responders and fire departments in the loop about any chemical that is considered hazardous. So it is our practice to recommend that whenever we can. So this is a diagram of, I guess you could call this either a real system or a theoretical system. I'm going to show you some pictures here. But what we have is a schematic of a propyl glycol for the medium temperature and carbon dioxide for the low temperature type system. So I'll just get into this a little bit. The line that I'm pointing to here be that portion of the system that would be located on the roof. This line is the carbon dioxide skid, which could be located on the roof or within the building. And of course, these are your, and that would be located throughout the various parts of the store. So the labels there, but I'll get into this a little bit here now. In this concept, a number of limit charge modules would be used to the load of the store. You can see that you could any number of these modules to create the capacity that you need. And in this case, we're showing 2 modules for the low temperature system. That would be ice cream freezers, various freezers, and this side would be 2 modules for the higher temperature systems. Getting in module a little bit, what I'm pointing to now is the ammonia compressor. And while my arrow's there, I'd like to touch a little bit on what Kayla was talking about regarding technology for the compressors. The compressors are currently available, and they are usually applied to much larger systems. I believe that there are some manufacturers who are developing semi-hermetic drive compressors, and scroll technology for hermetic constructions is also being looked into. I believe that a Japanese manufacturer has developed this, and reiterate what Caleb was saying, use copper in a system is not allowed, but what manufacturers are doing now is looking at using aluminum windings, and also using a miscible oil along the system. I bring this up because typically ammonia systems reject oil, and that is because the oil used is not miscible with the ammonia, and it has to be drained off. There are some new oils that are developed. But
I'm sorry, Eric. I'm just gonna. We're getting some background noise again, so I guess somebody joined late and wasn't here when I muted all the lines. So I'm just gonna mute all lines again, because it's now 3 or 4 times, and then you're gonna have to press #6 so we can hear you again.
Okay.
Go ahead.
Okay. Am I with you?
You're with us.
Okay. So back to the oil. These systems are really small charges in any case, and the oil actually pass through and be recycled. So I'm saying is traditional methods of oil management in a industrial situation are being addressed. Let's see here. I think that's all I had to say about compressor technology. Moving to the heat exchangers, what we're looking at here is the high-side heat exchanger, which takes heat from the ammonia and rejects it to water, which in turn is to in this case it would be a fluid cooler. Imagine that there would be a couple of different scenarios that could be used, and manufacturers would, of course, be the way they wanted to do it, and also consider what the owner wants. But for example, you could have ammonia discharged to an evaporative condenser, or it could even discharge to air-cooled condensers. In this case, we're showing through these lines and through these heat exchangers that the heat from the ammonia is being rejected to or glycol or whatever might be the coolant voice here in a fluid cooler. So to the cooling portion here, so obviously we would have the refrigerant shown here by the green line would go to the case it would be the ammonia carbon dioxide, the heat exchanger, and in this case it would be ammonia to propylene glycol heat exchanger. But back to the low temp side, to the heat exchangers, multi-channel heat exchangers are becoming cheaper, more prevalent because of manufacturing techniques, and this is allowing the industry, both the industrial and the commercial industry, to create houses with a much smaller footprint and still be very efficient. So coming out of the this this heat exchanger that I'm important to here is the condensing portion of the carbon dioxide for the temperature system. So what happens, of course, is the gets compressed at the compressor, it's condensed at the condenser, and then serves as the condenser for the carbon dioxide. This is what is known as a cascade system. So you can see where I point with my arrow here, a thermal expansion valve, and that's the pressure drop to create the cooling effect. So carbon dioxide is condensed in the exchanger, routed to a reservoir. And in the reservoir is a combination of carbon dioxide gas and liquid. And that liquid is then routed to a suction heat exchanger to increase the efficiency. And then it's further routed to the case. This is a solid valve, and you'll see a number of expand valves here. So, this is just a typical expansion process where high pressure liquid is expanded. The evaporator picks up the heat from the case, and a combination of liquid and gas is returned back to the heat exchanger, pass through the liquid suction heat exchanger, and the gas is then recompressed and routed to the condenser again. On the side, it's a much simpler system.
Sorry, Eric, I'm going to have to break it. We're really behind.
Okay.
I know that you have 7 or 8 more slides, so maybe you can skip all of this about the technology. Theoretically, these drawings, they'll all be available on the website. If you can just skip the actual stores.
Okay, we'll do that. Let me just touch on the propylene side here. Main difference in this case is of course, that the propylene is doing the cooling rather than carbon dioxide. It's operating at a higher temperature, and the technology is very much the same. So moving on, this is a different possibility where only carbon dioxide is used. Low temperature, it would be the same system, but for the medium temperature, what's the term you called here, Bruce? This is it's a high pressure feed, but evaporated brine system. That's what it's called. And the difference is that both liquid and gas return back to the receiver, basically due to the change in density of the gas. And
Okay,
the stuff
sorry.
is
We go. Okay.
yeah, there we go. I'm with you, Keely. I know we got to go. This is an example of a supermarket that actually employs an ammonia and carbon dioxide system in Australia. In 2008, that's 2 modules. Low temp is 112,000 BTUH. The medium temp is 850,000 BTUH. There are 2 flooded modules on the roof for the primary system, and the carbon dioxide system is in a mezzanine below. Considered fairly large modules. Of course, one idea that's floated around is that the charge be limited to 100 pounds, so there would never be a possibility of having to report a leak to CERCLA or the EPCLRA. Again, photos, this is the carbon dioxide skid that would be located in the store or optionally on the roof. Here you have lines to to the chiller. This is the separator. Here you have the CO2 pumps and the CO2 compressors. Next. And this is the CO2 skid system in the store, and you can see various components already labeled there. And a few more view that same system. And this is an example of a scenario where the equipment is actually on the roof in an enclosure. In this case, the enclosure would be something like a mechanical room. Other items that manufacturers we think would consider would be weatherproof cases, much like rooftop equipment is, typically seen, and also enclosures with removable panels, so that you essentially have the operation as door application. This is the chiller skid. This is not actually a brazed plate heat exchanger, but this is actually more of an industrial-looking system, but a commercial system would look very similar to this. Here we have the separator, and this would, in this case, be the ammonia CO2 condenser. And moving on a little bit, this is an example from Japan, an installation in Japan. My mom has developed some CO2 and ammonia glycol package systems, and you can see that there are a number of these units, weatherproof housing type situation with the scroll compressors that we mentioned before, the cool chillers. And it's notable to point out here that Japan is a nation that is prone to earthquakes, and yet they are still implementing the idea of using ammonia systems for supermarkets. I think that is a rather telling scenario that they will do that. And that's the end of my part of the presentation. This is our info. Bruce, President, Eric Smith is me, and of course we have Keely and Caleb. And I'll hand the ball back over to you, Keely. Figure out how to do that.
I'll do it. You don't have to do anything.
Okay.
I've got it all under control. Okay, great.
All right.
So we'll open it up to questions now. Thanks very much, Eric. I appreciate it. Ammonia technology is a new area. Well, not necessarily new, but it's I guess ammonia is an old refrigerant, but in terms of U.S. supermarkets having ammonia technology, it's fantastic to know that we have an organization like IIAR to share information with. So I appreciate it. If anyone has any questions, go ahead and hit that hand button on the lower hand corner of your screen, and I'll call on you. I can't believe that with a technology like this that there aren't any questions at all. Mark Mitchell. Now, since I have everybody muted centrally, you're probably going to have to press #6 to unmute your phone to ask a question. So, Mark, go ahead.
Can you hear that?
Yes, thank you.
I just had a question about the fluid cooler. If there's been any thought given to using that to reheat stores or to heat hot water?
Let me say first of all too that the question and answer period, it's not just the presenters who can answer the question. if anybody else has input, this is meant to be information sharing among all of the participants. So I'll give the presenters the first opportunity to answer if they have one, and I'll ask anybody else that that has something to say to answer the question to go ahead and jump in. So, or Caleb.
Okay. For Bruce, I'm going to repeat the question, and the question is has concept of using, and correct me if I'm wrong, questioner Mark, has it been considered to use discharge heat to reheat, to heat water, you know, this sort of thing? Is that right, Mark?
That's correct.
Okay. The technology in industrial applications actually is there. I don't believe that it has been considered for markets yet, but I think that's a very good thing to look into. One drawbacks is the quality of the discharge heat is it's not. How can I put this? It's not really hot enough to do a lot of work. So what is needed is actually a separate subsystem to increase quality of the heat, such that the temperature difference of the water and the discharge gas is greater.
Okay.
I'm not so sure that it would be economically feasible in a supermarket situation. So in other words, some additional equipment would have to be bought, and that would have to be weighed against, you know, for water heating.
Let's move on to the next question. I have Al Smith. You're going to have to press #6. We can't hear you yet.
Do you hear me?
Yes.
This is George Kazatsky.
Oh, okay. Well, wait, sorry, Al Smith has his hand up. Are you registered as Al Smith?
This is Al Smith.
Okay, you put your hand up, and we're gonna wait for. I'm calling on Al Smith, and let's let him ask his question.
Okay, I'll silence.
Al, go ahead.
Thanks much. The question is concerned to relief equipment dealt in some jurisdictions that required what's called a sparge line, which is a piping system below the reverser safety relief valve that exits the building, so the fire department can open the valve to dump ammonia into the atmosphere through a device that has a fire hose connected to it. Have you done any research and or findings on that type of system?
Kay, do you have any input on that?
Done any research on I think Eric, would that be a diffusion system or a
Yeah, I'll have Bruce answer this.
Yeah, this is Bruce Hedger. We've done some work empirically on the dispersant tanks that have been used in industrial systems. With this quantity of ammonia, we're talking about such a small quantity, and it being so quickly that I don't see the necessity to do this, particularly with a lighter-than-air refrigerant, which would disperse up, and we would recommend that the packages have a vent extend above the package and directly up to the atmosphere, as we do in industrial systems, so that we have a high-velocity discharge going straight up and helps with the dispersion into the atmosphere. And with ammonia of this quantity going into the air with that volume, the likelihood of ammonia being at ground level would be dramatically almost eliminated. So I can't see the benefit of any kind of sparging type system which would enhance the remove the ammonia to a lower level. It seems like that would be absolutely
counterproductive. Yeah. Okay. Are you able to, Bruce? Are you able to stay on the line to answer questions?
Sure.
Oh, excellent.
Yeah. Again, this is Al Smith. All of your thoughts are great, but we got a one-story supermarket or a one-story facility next to a five-story high-rise building. The fire departments intend to get quite nervous.
Yeah, and I understand that. That's what dispersion tanks are there. That's why there is that alternative.
You're talking about a dispersion tank.
Right.
I'm talking about a dispersion line that's flooded by the fire department. Entirely different thing.
Yes, it is. But the fireman's dump box and the dispersion and the line that you're talking about is a processed version of the dispersion tank. I would put it that way.
That's correct. That's a good way to put it.
What would need here is a relatively small water dispersion tank, which would be capable of taking the entire charge of the system. And in doing so, you create a closed loop, automatic version of what you're talking about that doesn't require the fire service to create a manual release. It's already done. It's already part of the system, and it takes care of the overpressure. And because we're talking about a refrigerant, we are dramatically reducing the pressure behind that release so that as you begin to release the refrigerant into the dispersion tank, the pressure is equilibrated down to and below atmosphere, and you don't have the ability to release that pressure any longer. It simply won't go out of the system. So in all respects, I would think that you could put in this dispersion tank, which is really the automated version of what you're describing.
Okay, let's move on to the next question. Sam, I think you were next. You have a question for us?
Yes, this is Sam. I don't specifically have a question, but would just like to chime in a bit in regard to the question that was asked by, I believe it was Mark Mitchell. In regard to
about heat reclaim?
Exactly, yes. And speaking on behalf of use of ammonia on the industrial side, heat reclaim is often put into practice in a couple different manners. Off of the compressors, tapping into the external oil coolers on the compressors, whether it's a screw compressor or a reciprocating compressor, that's often done. And then as well, grabbing a little bit of the superheat off of the discharge of the compressor discharge before it would go on to the condenser. Some superheat can be obtained there. Now, in both of those cases, it's tapping into essentially the 10 to 15% of the total heat of rejection that be discharged from a compressor. Technology is rapidly developing that enables the use of compressors to take the discharge pressure to much higher levels, corresponding to much higher temperatures, for full heat pump duty and full reclamation of the total heat of rejection. So there's a lot of advancements that are going in on the industrial side. How that would convert over to the commercial uses, I guess, is yet to be seen.
Okay, thanks very much for the input. Georgie, we're coming down to the end here. You have 30 seconds.
Hey, I just want to make a contribution to the same topic by stating that water heater, heating of discharge and condensing heat for water heating has been broadly used in supermarkets, way to increase the efficiency and to supply water. And ammonia is particularly good for this because the discharge temperature is with ammonia is way higher than with the other refrigerants. So if this has been used with refrigerants like 4A and 507 with much lower discharge temperatures, with ammonia it will be much more beneficial. The negative side is that it increases the charge of ammonia. We know what is the consequence. The desire is to have as small charge of ammonia as possible. And one more contribution, that in addition to aluminum windings compressors, there are also so-called canned compressors, semi-hermetic for ammonia. My 10 seconds are over. So I'm
Thank you. Thank you very much, Georgie. I appreciate it. I got I have a question here that I got over the chat function, and it's a multiple part question. Has anyone studied the general suitability of supermarkets for conversion to an ammonia system? Do stores have the egress requirements from their roofs for an ammonia system? Do store roofs have the load capacity to support an ammonia system's weight? I was unclear if more equipment would be shifted from inside the store to the rooftop in the system shown. Maybe, I'm not sure, Caleb and Eric, but maybe since this is a question that specifically deals with supermarkets and roofs and loads, maybe some of the equipment manufacturers might have some feedback on this. Anybody jump in?
This is Bruce. One of the things I should point out is that many, if not most, of the supermarket chains have cold storages and even food and beverage processing operations themselves, most of which are using ammonia. So there is technology there, there is engineering capability there, and I'm quite confident that they're cognizant of all the requirements for an ammonia refrigeration system industrially, and they would be able to apply those kinds of considerations to things like rooftop egress and other kinds of things, just as they do for their own installations that are on the processing and storage side. So while I think there are considerations here for the various locations, we're dealing with companies that are familiar, perhaps in a different department, but they're still familiar with all of these applications, just not in the supermarket setting. They just need to convert the thinking over to applying it to the supermarket.
I think there are a lot of supermarkets, currently that have their entire machine rooms on the roofs.
They certainly do.
Yeah.
Kiwi, Rob, I could probably address that real quick. This is Rob Arthur.
Okay.
In like the question was in an existing store scenario, and that's just a store base. We do a lot of projects where we go and add equipment to the roof, or even facilities that not have refrigeration previously. Now they're adding refrigeration and using existing structure, and maybe you just have to have a structural engineer review the locations you can put that equipment in. In some cases, you have to go in and add columns or beef up the structure to make it work. And as far as accessibility, typically most all grocery stores or even retail facilities have a roof access, roof hatch with a ladder up to there for service. Some are better suited and the equipment to go up there a little easier, but basically on a store-by-store basis, and it's done today with other equipment that that'd be similar to the size of an ammonia system.
Okay, great. We've reached 3:30, which was the official end of the webinar. I have my next meeting at 4 o'clock. If anybody does have one last question, I can certainly stay on for another couple minutes. But for those of you who have to leave at 3:30, I wanted to say thank you very, very much for attending. This will be available on the Green Chill website, and you'll have our contact information. Feel free to contact any of the presenters. And feel free to contact me, of course, not just for your ammonia-related questions, but for anything related to the Green Chill Partnership. Again, thanks for attending, and for those of you who do still have questions and would like to stick around, feel free to do that. I'm just going to give another minute or so. I see I still have Sam's hand up and Georgie's hand up. I'm assuming that that's left over from your previous questions, and that you have another question. So if that's not the case, let me know. Other than that, I don't actually see any other hands up. so don't get somebody asking a question, and then in it we will call it to end. Oh, there we go. Billy Shuttlesworth. Bill, we're going to have to press #6.
Keely?
Here we go.
Okay. The question I had was the two sample stores that they showed, what type of defrost did they use on the low temp cases?
Okay. Does anybody, I think some of you out there have visited those stores. I'm not sure who can answer that question. Caleb, do you happen to know?
Which picture was he referring to?
Well, the stores that were shown was the Australian store, and then there was the Japanese store.
Yeah.
Electric defrosting store for the CO2 side of the system.
Okay. That's what I thought it probably was, but I just trying to make sure. I think this thing that we'll be faced with in this is the technician training, because the majority of technicians out there now are, are refrigerant techs. Now we do have our house facilities are ammonia, and that it's a completely different group that takes care of that. Those takes care of our retail stores. So it's you got the in-house techs and you got the outsourced techs that would definitely be trained where you got a couple hundred stores to deal with.
I know that I was actually last week I was invited to speak about green chill at the yearly Train the Trainers conference for the United Association, which is the union for pipe fitters, plumbers, HVAC and R technicians, and they are really up on all of these new technologies, and they're incorporating a lot of information about these new CO2 technologies for supermarkets into their regular trainings. Their apprentices have to take 2 hours of extra training every single week for the 5 years of their apprenticeships. And I did a small part of my presentation on ammonia technology, and they were already aware of all of this stuff and already incorporating this stuff into their trainings for Certec apprentices. So I think that's a good sign related to what you were just talking about. Obviously, it's not enough, but at least that
it's also worth pointing out that that good deal of the maintenance, probably 80 or 90% of the maintenance for a supermarket system is for the cases and the copper tubing and the fitting leaks. So I think the feel is that there's not a huge difference in technology for the actual refrigeration system, and that can easily be overcome.
Great. Let me call on George Ron from out in Minnesota. You have a question?
Sure. Thanks, Keely. Being, a HCFC, HFC trained refrigerant person, I'm kind of ignorant to ammonia, I have to admit that. Obviously, the consensus on the call is that the toxicity levels wouldn't be achieved in some of these systems that we're talking about, 100-pound, 200-pound charges. But curious about the dispersion of the odor, particularly in areas where we have residential neighborhoods backing up to the stores. What kind of an impact is that? How big is the odor dispersal as opposed to the simple toxicity dispersal?
This is Badger. We run tests in cooperation with the Ammonia Safety Training Institute out at Fort Ord in California, and we have a few videos and things that we've shot. But we use gas detectors, and obviously the nose is a pretty good detector, as you point out. And when we're running these tests, we notice that when you're upwind and still very close to the ammonia as it's being dispersed into the atmosphere, you don't have any reading on the detector, nor can you smell it. This does not immediately disperse throughout where someone would be standing. This is not like the synthetic refrigerants where it hugs the ground, disperses along in a kind of a flat pattern, and it depletes the oxygen in that area. That's not how this refrigerant works. It goes straight up into the atmosphere, and the only exception to that would be a foggy day where you've got a cloud, literally have a fog cloud, and the ground level, and the ammonia is being absorbed in the water molecules of the fog cloud. But generally speaking, it'll go straight up and away from your nose, and you won't be able to smell it. It's pretty difficult to smell, and 5 parts per million is pretty low, and frankly, most men can't smell it until it gets about 20 parts per million. I still don't know the reason why women can smell it better than men can.
Oh, I have some theories about that, but we also I'm not sure if Cynthia Gage is still on the line. She's kind of our refrigeration guru at EPA down in Research Triangle in I can never remember which one of the Carolinas it is, but I've been talking to her recently, and because ammonia is going to be such a big topic for the future, at least we think. We've been talking to Cynthia and her team about doing some plume modeling for EPA. I don't know if Cynthia is still on. If you want to say anything about that or have anything to say, I know that in general, some other people working on this topic are also working on plume models. Okay, I don't hear anything from Cynthia, so maybe she's off the line. Bar on, Cynthia. It's you have to hit #6.
I think I did it. Am I?
There you go. Okay. Yep, you're on.
I really, it's a work in progress, so I really don't have much to say now. But just to confirm what you've said so far, we are looking at this.
And obviously, I know that the even with regular refrigeration systems, I mean, I get calls, all the time from partners that have stores in particular communities where the guy who's doing the permitting, doesn't understand, what glycol is in a secondary loop system. So there are certainly going to be huge differences in the levels of knowledge and concerns, based on where each and every store is located. And I think, what we all know, regardless of the technology, you have to stay in close communication with the people you're dealing with on a local level, find out what their concerns are, and it's not difficult to do plume modeling using the specifics of a particular site. But our goal, just to start off with, is to do some general plume modeling that talks about a typical scenario and also, what would be the worst case scenario. So, for instance, what Bruce was talking about, even if you have 100 pounds of ammonia and something falls out of the sky and you lose all of the ammonia in, line of 10 self-contained units, and there's a big cloud, and you're surrounded by 5-story buildings, what is the scenario there? So we're thinking about typical scenarios and worst case scenarios. And I'd love to have your feedback, if you guys have, if especially Green Chill partners, if you have other wishes in terms of, helping us ease the way for some of this stuff for you, I'd love to hear from you. So I'm just looking here. I think everybody had a chance to ask their questions. I guess I'll do a final call. All right, the people who had their hands up, I think they already asked the question. So I'm gonna end it here, and thanks very much to all of you again. Appreciate your flexibility to be able to stay a little bit longer. And please watch for the notice for next webinars. If you'd like to be added to our webinar invitation list, just send me an email. We're happy to add you to our standard list. And if you don't belong to Green Chill's LinkedIn group, please go to our homepage, www.epa.gov/greenchill. And on the homepage, there's, to the right of the screen, there's a new box with the link on how to join the LinkedIn group. We post all of our announcements for all of our webinars on that group, and we post a notice on there when the webinar is available on the website. It's one of our main communications tools, so please sign up for the LinkedIn group. We hope to see you at the next webinar. Thank you very much for attending, and have a good rest of the day. Bye-bye, everybody.
Thank you.